Eat glucose to get into our body, and some of it is absorbed through mucous membranes, but most of it's absorbed through our small intestines.
Nice.
And then it is transported through the blood, and our pancreas is kind of our thermostat on if the glucose levels are high or low, and when they're high, it releases insulin, and the insulin helps to transport it either into the fat storing cells, into the liver to change it into glycogen, or into the muscles to be used. Anybody want to continue that those words?
Well, and if once it gets into the cell, if there's oxygen added to it, then it can get into the mitochondria to produce ATP. But if there is no O2 involvement, then it begins to ferment, and then it gets transformed into lactate, or lactic acid, and then redistributed back out of the cell.
Glucose moves into the mitochondria?
No, glucose through glycolysis gets pyruvate.
Pyruvate, yeah.
Pyruvate. With O2 added into it, gets into the mitochondria.
But glucose turns into
What else we know?
glycogen way before that.
Glucose is stored as glycogen in the liver. Can we talk about that? And glucagon causes the stored glycogen to convert back into free circulating glucose in the bloodstream. Your body regulates it between meal times so that it can keep that blood sugar at a relatively consistent level in a healthy individual.
Okay. Anything else?
It needs insulin to get into the cells through facilitated diffusion, but if the insulin is not there, or with type 2 diabetes, the receptor changes, and so it doesn't recognize the receptor anymore. I mean, the insulin anymore. And so
What's the transporter
Insulin.
at rest? What's the transporter at rest?
Is it thiamine?
Hmm?
Is it thiamine?
What's the facilitator?
Beta cells?
Hmm?
No. I'm missing
Blood?
Oh, the blood. The blood stream.
Four.
Maybe? No.
GLUT4 transporter. The GLUT4 transporter is the facilitator.
Oh,
Where is the GLUT4 transporter
she said that word.
normally?
I'm trying to be more.
Where? Where is the GLUT4 transporter typically?
You doing okay there? I'm fine.
Muscle
Is it
cells,
really bad?
Where in the muscle cells?
submembrane.
Where is the GLUT4 transporter typically?
In the body.
Well, we're down to muscles. We're down to muscles.
Technically, that's right.
Inside the cell waiting to be put on that.
Where inside the cell?
Are they called vesicles? Like, wrapped in pieces of cell membrane?
Are they?
I don't know.
How does the glucose get in? How does blood-borne glucose get into a cell?
With insulin.
Facilitated transport.
Through channels?
Does it go through channels?
Yes.
Wait, what's your question?
That's
Does it go
that's
through
no.
What was your question again?
How does
How does glucose get into cells?
It's not absorbed into cells, and so it's got a
What were we just talking
Diffusion.
about?
facilitated
Facilitated
Diffusion.
And
transport.
what's the facilitator?
Insulin.
G4.
What's the facilitator?
GLUT4.
The GLUT4 transporter.
GLUT4.
So now I'm back to a different question about how it gets into the cells. So how is it getting into the cell at that level?
Does the insulin activate the GLUT4 transmitter to allow glucose to go in?
Josh?
That's a no.
I've worked with him long enough, I know his nose.
So the discussion that Josh and I just had is that the GLUT4 transporter is typically where? We didn't like put a period on it, but we were close. Where is it at, typically?
Inside the cell.
Inside the cell, in the cytosol. It's floating in the cytosol. What's cytosol?
Something inside the cell.
What is cytosol?
Is it cytoplasm?
The matrix within the cell, the fluid of the cell. Okay. But the GLUT4 is a what? What's its full name? The GLUT4.
Transporter.
Thank you. Which means it's got to do what?
Transport
It's
something.
got to transport. Where's the sugar? Where's the glucose?
Outside of the cell on the
Where's
cell.
the G4 transporter?
Inside the
Inside
cell.
the cell.
So my question is, how does the glucose get into the cell?
Insulin triggers the gates that open up.
What gates?
The-
A gate on the membrane.
Doesn't
So
it
sorry.
just make
What
the
is an
cells more
insulin receptor?
permeable?
What is an insulin? It is a type of receptor. What type of receptor is it?
It's a chemically mediated channel.
Chemical channel.
Yes, Andrew?
Sorry, it's totally coming.
Keep going.
Not a voltage gated, right?
Chemical gated.
Yeah. it's,
Well, we've said chemically gated a couple times and Corey hasn't said yes, so
has to do with the metabolism. The insulin unlocks the gate. It's so not there.
A facilitating.
What is a camp?
Is it a? Chemistry is the answer.
There's a name for the subset of receptors of which insulin is one. I'll give you a hint. Muscarinic receptors, beta receptors, and alpha receptors are all the same thing. They're not the exact same, but they all fall into the subcategory of them. Any ideas?
Is it like a key, like a facility?
Is it a G protein coupled receptor?
There we go.
Josh!
Can you say it louder for the folks in the back? No, I really didn't hear it though. What was it?
G protein.
Coupled receptor.
coupled or so.
Sorry.
It is a G protein coupled receptor. What's a G protein coupled receptor?
Doesn't it change? Yeah, it changes the.
On the inside of the cell.
Something changes them.
What chemical would change it to open or
Yeah, as opposed to just opening it with a locking
To-
key, it
to
changes
twist to
the
open.
matrix of the channel, doesn't it?
So they
the G protein coupled receptor, insulin? Well,
We haven't got that far yet.
if beta receptors, muscarinic receptors, and insulin are G protein receptors, then we already know that when that chemical comes in and hits that receptor, it allows it to twist, and whatever it is, it's allowed to go through.
So are we saying, in this case, it's allowing insulin or glucose?
Then glucose into the cell. But the G protein coupled receptor opens and allows
Okay,
glucose in.
what does that mean? What does a G protein coupled receptor do? What does a G protein coupled receptor do? It's a second messenger system.
There we go.
Okay, you guys gotta get past thinking everything is gated. Things don't always just come in and out. There's other things that happen. It looks like we need to talk a little bit about G protein coupled receptors. Do you guys
Happily.
remember those words?
I remember those words when you say them.
Oh, it's,
Okay.
it's your shoe,
You guys-
not my shoe.
Do you remember what the benefit and or point of a G protein coupled receptor is?
It's the trigger, the transporter on the other side to.
Globally, what the point of a G protein coupled receptor is? No?
Is it to
So when we open a channel, and that facilitates the exchange of ions, for example, right? What's it based on? A gradient, right? You open the channel, and whatever's going to happen is going to happen, right? It's for all intents and purposes, it's an all or nothing. It just happens to be with whatever the gradient happens to be, right? So if we open a sodium channel, and assuming the person is normal, sodium's gonna make the exchange. There's nothing we can do once we open that door to that channel, we're out of the mix now. We've opened the floodgate. It's gonna happen. Does that make sense? But to create a second messenger, it means you're going through a chemical process to eventually create something that'll lead to an action. And because you're going through a cascading of chemical reactions, you can influence that anywhere along the way. Does that make sense? Mm-hmm. So we can initiate something, but our body can stop it along the way. You can't open a channel and then stop the flow of ions. You open the channel, it's going to happen. But a second messenger system, there's places along the way that you can influence what's happening to get a more finite control over what that second messenger is going to do. Does that make sense? I think we better look at an example of that in just a little bit. Okay, so what else? So it's a G protein coupled receptor.
Mm-hmm.
What is that G protein? What is the second messenger in this case, in the case of insulin, going to do? We'll just skip to that part.
So the insulin is what triggers the channel to open. Is that what we're saying?
Stop.
Well, how did insulin get in here?
Stop. Is the insulin receptor on a channel?
No.
Get past that word.
That's
It's not a channel, right?
Will you draw a picture
Will I draw a picture of a channel?
of what we're talking about?
okay. Sorry. Were we saying that I apologize. So were we saying the insulin triggers the receptor, the G protein receptor?
I'm with you
Yeah,
on
and
that.
insulin is a ligand.
Okay.
What's a ligand? Insulin is a ligand.
Is it
What's
like
a ligand?
Key?
The key. What's the receptor?
Ligand key.
What's the receptor?
Glute,
G protein.
glute
I'm
4.
not saying anything about G proteins. I'm saying receptor. What is a receptor?
A hole.
Like a lock.
Yeah, lock and
I'm
key.
looking for you to use the word key so that
Lock and key.
that's the lock.
So ligand is the key to the lock.
What is the receptor on?
Cell membrane.
It's on the cell.
So what on the cell?
Cell membrane.
G protein.
Sometimes on a G protein
Oh, I see.
that is coupled with the receptor, or in this case, it could also be on the word that I didn't want you to use previously,
A channel.
a channel.
Haha.
It could also be on a channel, right?
Yeah.
You understand? It's on a protein of some sort. The channel is a protein that goes through the cell membrane. The receptor is on that channel. The G protein is something that's on the inside of the membrane, and it's hooked to that receptor. The receptor is always the thing that takes in the ligand, whatever the chemical is, or will activate based on charge, or whatever the case is, right? Does that make sense?
Mm-hmm.
So what are we talking about in this case? What was my original question to you?
Glucose. How does glucose get into the the GLUT4?
How's
How do
In the cell.
GLUT4 and glucose
meat?
meet?
Fantastic. So we have a GLUT4 transporter that's hanging out in the cytosol. We have glucose that's hanging out outside the cell. And we know that insulin engages a G protein coupled receptor that's going to lead to a second messenger. The second messenger is going to do what in some fashion?
Going to cleave off gamma from alpha beta and cause the gamma protein to bond with cyclic AMP.
Okay, so that's what's happening. That's what's happening on the G protein coupled receptor, but that's pre-second messenger. Now we're at the second messenger.
So
I skipped a bunch of stuff on
that
purpose
fun stuff.
because we were dying.
Dying.
So what has to happen?
It makes the
The influx of
GLUT4 go to the cell membrane.
It makes the GLUT4 bind to the cell membrane, right? And then it becomes what? What's the word for what that is going to do? Because now it's on the inside of the membrane, and what does it need to be?
Unlocks the deadbolt.
on the outside of the membrane. So it has
Does it need to be on the outside? Does it need to be on the inside? Where's
Need to
glucose?
On the outside.
on the outside. It has to make a
Okay.
bridge
So what does it have to be?
in between.
What do you mean in between?
Has to create that bridge between the inside and the
So
outside.
what do we call that?
Channel.
Say it.
Channel.
We're just so afraid.
We're so easy.
Like a bad word.
What's it called?
Ligand?
No, no. That's insulin.
But it plugged into a G protein.
How is this gonna get through this being my cell membrane?
Like a protein.
Through our ligand gated,
A what?
our, never mind.
What are gates on?
Gates are on channels.
Do we have a channel?
No.
Well, in that picture, you know.
Have we discussed channels? Have I not yelled at you enough for saying the word channel when we're talking about a protein coupled receptor?
We talked about channels briefly.
G-force changes the shape
Of what?
of the G protein to where it opens up. Cause isn't it like a physical?
The G
thing?
protein, okay, so I need a few more minutes. Are you guys okay? We need to deal with this G protein thing.
Yes.
So we've been talking about I'll try to keep this really brief and just give you an overview for right now. We need to deal with this G protein thing and making sure you kind of understand what's going on. Muscarinic receptors, beta receptors, and alpha receptors don't work the same way as nicotinic receptors, right? Nicotinic receptors are channels. The receptors are on channels. The receptors activate gates that are on channels. Does that make sense? That's not the same thing as the second messenger system and how the second messenger system tends to work. So, I don't know. I'm not gonna do that. We're gonna go to this. Okay. So this is the cell membrane right here. Okay. This is the receptor, and then we have a G protein. G protein have three subunits on them. There's an alpha, a beta, and a gamma subunit that are on these G proteins. That just means a G protein are these three subsets of proteins that are bound together and bound to a receptor. And the receptor is transmembrane. What does that mean?
Across the membrane.
Across the whole membrane, okay? When a G protein coupled receptor is activated, you have a ligand that binds to that receptor. When that ligand binds to that receptor, the receptor physically changes shape because now it's holding on to something different. Does that make sense? It's like taking a bag and putting something in the bag. The bag had a shape, and now you put something in the bag, and the bag has a different shape. Does that make sense? Mm-hmm. When that bag creates a different shape to it, what it does is it moves this G protein in such a way that that alpha subunit has a GDP on it. You guys know ATP, right? Which is adenosine triphosphate, right? This is guanine diphosphate. The phosphate can be interchanged between adenosine and guanine, and they do the same thing. So as an overgeneralization, wherever I can use ATP in the body, I could use GTP as well, right? It's a different amino acid that's kind of holding it together, but it doesn't matter, okay? This is called the G protein coupled receptor because of the guanine. When we make that, when the ligand binds and it changes the shape of that receptor, it ends up allowing that alpha unit to exchange a GTP that was previously being held to it with a GTP that is in the cytosol. Does that make sense? When the GTP then is now bound to that alpha subunit, it causes the G protein to break apart. And the alpha subunit is now broken apart and moving on down the line within the cytosol. And the beta and gamma units stay together and they are broken apart. And now those two subunits are free to do things. The alpha subunit starts to break apart the GTP. It starts to break apart one of the phosphate groups. Now that it's by itself, it has an enzyme that starts to break apart that phosphate group, and it resets the GTP. If you pull off one of the phosphate groups of a triphosphate, then you're left with a diphosphate. And so that's how the GTP gets back to the alpha unit. Now that alpha unit, if it comes back into contact with the receptor and the beta and gamma unit, it rebinds back into its original G protein. Does that make sense? This alpha and beta subunit collection is now free to go do something someplace else, to act someplace. Okay? That's it in a nutshell on how the G protein works. But it's what this beta and alpha subunit do that become pretty important. And there are a couple of different possibilities for what it does. One possibility is that alpha and beta subunit will, well, we've got two different things going on here. This break apart of what these will do, one thing that it can do is it can activate another protein, okay, that will cause a second messenger system to occur. What you see right here, and I know it's busy, and I'm not going to hold you to it, so just relax for a minute, is the production of cyclic AMP. This is how beta receptors work. Beta receptors will eventually cause the production of cyclic AMP that will then work inside the body somehow, right? So, for example, or alpha receptors, the same thing. Let's say the beta-2 receptors that are on the coronary blood vessels. There are beta-2 receptors on coronary blood vessels. Those beta-2 receptors will produce cyclic AMP that will work towards the activation of our calcium ATPase pump on the SR. The calcium ATPase pump on the SR will then be it will work faster and will start to pull all of the calcium back into the SR, which does what to the muscle? What will it cause the muscle to do? Relax, right? It'll cause the muscle to relax. So that's one thing that we can have happen. It's this second messenger here that causes things to occur. That's one of the second messengers. Here is another different type of second messenger. Phospholipase C, PLC, is a completely different second messenger that does different things also. So it's that second messenger that causes the problem. Do you understand it's not a channel? It creates a chemical reaction. And if I have this kind of a reaction going on, where I have all this big giant concept map here, there are different places along the pathway that my body can interact and cause things to occur, right? So, for example, this pathway that you see right here in an endothelial cell. What's an endothelial cell?
Lining, tissue lining.
Of, what is an endothelial cell? Not an epithelial cell, what's an endothelial cell?
Inside.
Of what?
Lining.
When we say endothelial cell, you should be thinking exactly one type of cell. What kind of cell? What's that? Blood vessels. It's the cells of the blood vessels. Okay? This is going to occur in the cells of a blood vessel. Okay? Not the muscle of the blood vessels, the cells of the blood vessels. In the cells of the blood vessels, this is going to occur, and this process right here is going to lead to the production of nitric oxide. It's called endothelial-derived nitric oxide. That nitric oxide is a gas that is going to move through the endothelial cell into the smooth muscle cell, and when it's in the smooth muscle cell, the nitric oxide is a second messenger, not through a receptor, that is going to go straight to activating the PLC. And we're going to go through this process of relaxation. Two completely separate processes, right? But let me ask you this question before I go back to the other slide. What is Viagra? What is Viagra? What is its mechanism of action? What's its classification then? Not vasodilator. Yes, it's a vasodilator. If I were to ask you for a different classification, what classification is it in? It's a blah, blah, blah inhibitor.
It blocks the breakdown of nitric oxide.
It's a blah, blah, blah inhibitor.
Nitric oxide.
Nitrate inhibitor?
No.
CGMP?
If I'm looking at the commercial, it's going to say it's this kind of inhibitor.
ACE. No?
Nope.
That's a different commercial.
That's a very different thing.
Yeah.
Don't remember? It's called a phosphodiesterase inhibitor. It's a phosphodiesterase inhibitor. Do you guys remember that?
I remember you talking about it.
Great, so that's a
Yeah,
start.
that's about it.
It's called a phosphodiesterase inhibitor. Let me go back to that other picture. This is phosphodiesterase.
That's right.
Phosphodiesterase is an enzyme that takes cyclic AMP and inactivates it. Cyclic AMP is an active form of AMP, adenosine monophosphate. Phosphodiesterase is going to pull water into the system, into this cyclic AMP we have, and make it no longer active. In other words, this pathway is going to lead to the production of nitric oxide. The more cyclic AMP we have, the more production of nitric oxide we have. Phosphodiesterase will break cyclic AMP's ability to do that. Does that make sense? If we give a drug like Viagra, it's called a phosphodiesterase inhibitor. It affects that enzyme, so that enzyme is out of the mix now. Do you understand? If I activate a nicotinic cell, I open a channel. If I open a channel, boom, it's going to happen. There's nothing I can do about it because it's completely based on the gradients of those ions. Assuming the ions are normal in a person, if I open a channel, it's done. There's nothing more I can do. I can't influence that action anymore. The only action I have on a channeled receptor is action or no action based on the channel being open or closed. Does that make sense? Mm-hmm. But here's what I have in this case. In this case, I have a big set of chemical reactions that are occurring, right? So now, what I do is I have the production of cyclic AMP in the endothelial cell. I'm only giving you one example. I have the production of cyclic AMP that's going to lead to the production of nitric oxide. Nitric oxide is then available to to gas itself through the endothelial cell into the smooth muscle cell and cause contraction to occur, right? I have an enzyme in the endothelial cell that stops the action of cyclic AMP and therefore stops the action of nitric oxide.
Doesn't nitric oxide dilate the cell?
It does.
You said contraction.
I don't know what I said. It goes into the smooth muscle and causes dilation.
Okay.
Sorry if I said that wrong. It absolutely causes dilation. It's the most potent dilator that we have. Okay? This enzyme is going to stop that reaction and therefore stop the production of nitric oxide within the endothelial cell. But now we give Viagra, or they take Viagra. And Viagra is a phosphodiesterase inhibitor. Right? So if I have a phosphodiesterase inhibitor, I eliminate the ability for cyclic AMP to be broken down, to be inactive. That's not broken down, but to become inactive. Does that make sense?
Mm-hmm.
Therefore, in this cell, the cell that has been that has had contact with Viagra, only has the ability to produce cyclic AMP. It can't break the cyclic AMP back down again. Therefore, it will continue to produce nitric oxide. Does that make sense? So the only way that we have to prevent nitric oxide from being produced is to not engage the original G protein coupled receptor. That's the only thing that we have now, because we don't have the enzyme that breaks down that cyclic AMP. Does that make sense? In other words, we don't have what is this whole thing? Say it. It's a negative feedback loop, right? This is a positive feedback loop, coupled with this enzyme makes it a negative feedback loop. So the more cyclic AMP that we produce, the more active that enzyme becomes to break that down. Does that make sense? So traditionally what we'll have is we'll activate the G protein coupled receptor, we'll get nitric oxide because of the production of cyclic AMP. That production of cyclic AMP will activate the enzyme to break it down. And if we need more nitric oxide, we have to engage the receptor again. Does that make sense? That's typically what's going on. Now, in the case of Viagra, what we've done is we're going, okay, this person has some neurologic, I'm talking in the case of like erectile dysfunction. They have some neurologic or other issue that is preventing them from getting an erection. It's preventing them from going through this process to produce enough nitric oxide to cause the dilation of the penis and vaginal blood vessels to cause engorgement. So we provide a drug that stops this enzyme from working so that the net is that there's just more cyclic AMP and more production of nitric oxide. Does that make sense? Y'all get it? By taking out that enzyme. Now we provide them nitroglycerin on top of that. And what happens?
They're going to be, they can't stop vasodilating.
That's all they have left. Now we've given them a drug that does nothing but constantly stimulate the receptor, right? Because nitroglycerin